There's a photograph nobody was supposed to see, a white sphere, blurry and overexposed, captured by a Mars orbiter during a routine pass. NASA flagged it, classified the telemetry, delayed the public release. But the European Space Agency had already made copies, and based on it, they did something unprecedented. They activated a mandatory planetary defense drill without American approval, using data that wasn't theirs to use. The object was 3I Atlas, an interstellar comet. The response was political theatre. Or was it? Stay until the end, because the real question isn't what NASA saw. It's why Europe stopped waiting for answers and started preparing for impact. If you're as captivated by all of this as I am, go ahead and hit like and subscribe so you stay in the loop as more details emerge. Leave a comment letting me know where you're watching from, what time it is right now, and whether you think we're actually being told everything about 3I Atlas. Part 1. What just happened? In late 25, something happened in the skies above Mars that most people will never hear about, but that might quietly change the way humanity thinks about cosmic threats forever. The European Space Agency confirmed that its Mars orbiters had photographed an interstellar visitor during a close flyby of the red planet. This wasn't just another dot in the telescope. This was 3I Atlas, only the third confirmed interstellar object ever detected by human instruments, caught in the act of racing through our solar neighbourhood at speeds that defy the lazy orbits of our homegrown comets. For context, we've been watching the skies for centuries, cataloguing thousands of asteroids and comets, yet only 3 visitors from beyond our solar system have ever been confirmed. 3. That's how rare this is. And when you catch one of these cosmic wanderers close enough to photograph in detail, that's not just good luck. That's the astronomical equivalent of winning the lottery while being struck by lightning. But here's where it gets strange. Europe didn't just take pictures and file them away in some academic journal. They acted with speed and transparency, releasing data almost immediately after the flyby. Meanwhile, NASA, the agency that has dominated space exploration for decades, went oddly quiet. For weeks, there was radio silence from the American side. No breathless press releases, no high-resolution images flooding social media. Just silence. And in the vacuum of that silence, questions began to multiply. Why would Europe move so decisively while America hesitated? What did the European Space Agency see that made them act so quickly? And perhaps most unsettling of all, what does it mean when one of the world's major space agencies treats an interstellar comet like a rehearsal for something far more serious? The claim being whispered in certain circles is this. What Europe did wasn't purely scientific curiosity. It was a planetary defense test, a dry run, a way of proving that if something truly dangerous came screaming toward Earth from the void between stars, we could detect it, track it, image it, and respond, all without waiting for permission or coordination from NASA. It was a unilateral flex, a quiet declaration that Europe is ready to take the lead if America continues to drag its feet. And if that sounds dramatic, consider what it implies. For the first time in history, a non-Earth-based platform was used to monitor an interstellar intruder. Mars orbit became a surveillance post. Cameras designed to study dust storms and ancient riverbeds were turned outward to watch something that came from another star system entirely. Now, you might be thinking, this all sounds like the plot of a science fiction thriller. And you'd be right to be skeptical. After all, 3I Atlas is officially classified as a comet. It has a tail. It has a coma of gas and dust. It behaves, more or less, like comets are supposed to behave. But dig a little deeper into the data, and you'll find oddities. Strange spectral signatures, unusual polarization measurements, outgassing patterns that don't quite match what we expect from solar system comets. Nothing definitive. Nothing that screams alien probe, but enough to make a few scientists raise their eyebrows, and a few more to quietly wonder if we're looking at the full picture. And that's what makes this story so compelling. It's not just about a comet, it's about power. It's about who gets to decide what counts as a threat and who gets to respond. It's about transparency versus secrecy, cooperation versus competition, science versus strategy. Space is no longer a neutral frontier where nations collaborate in the spirit of discovery. It's contested territory. And 3I Atlas, whether it's a harmless ice ball or something stranger, has become the first shot in what might be a new kind of space race. Not a race to the moon or Mars, but a race to prove who can see the threat coming first. What you're about to hear is not just a story about astronomy. It's a story about geopolitics, hidden motives, and the quiet transformation of space agencies from explorers into sentinels. You'll see raw telescope images that reveal more questions than answers. You'll hear about spectral data that suggests 3I Atlas formed under conditions wildly different from anything in our solar system. You'll learn how a handful of spacecraft scattered across millions of kilometers coordinated to track an object moving faster than anything we've ever tried to intercept. And you'll be forced to confront an uncomfortable truth. The next interstellar visitor might not be so benign, and when it arrives, the question won't be whether we can see it. The question will be whether we're ready to act. This is the beginning of something new, a shift from passive observation to active vigilance, from astronomy to defense, from wondering what's out there to preparing for what might come next. And whether you believe 3I Atlas is just a comet or something more, one thing is certain. Europe just fired the starting gun. Now the question becomes, who presses record first when the next interstellar visitor shows up? And what happens if we're not all reading from the same script? Part 2. Recent developments, data release and what's visible so far. The flood of images began slowly, then all at once. In the weeks following the Mars flyby, a cascade of data started appearing from spacecraft scattered across the inner solar system. NASA's Mars Reconnaissance Orbiter captured a close-up snapshot on October 2nd, 2025, when the comet was roughly 0.2 astronomical units away. That's about 30 million kilometers, which sounds like a lot until you realize it's closer than we've ever gotten to an interstellar object with a high-resolution camera. The image itself is almost anticlimactic. A fuzzy white blob against the black void of space. A semicircular core surrounded by a diffuse cloud of gas and dust. If you squint, you can almost convince yourself you see structure. Maybe. But mostly it looks like someone smudged wit out on a photograph of deep space. Then came the ultraviolet data from MAVEN, another Mars orbiter, which detected hydrogen emissions streaming off the comet. Hydrogen means water. Water means the comet is warming as it approaches the sun, and its ices are sublimating into vapor. Perfectly normal comet behavior. Except the scale and distribution of the hydrogen cloud seemed just slightly off from what computer models predicted. Not wildly off, just enough to make researchers frown and add a footnote to their reports. Meanwhile, further out in the solar system, the Lucy spacecraft en route to Jupiter's Trojan asteroids turned its instruments back toward the inner system and captured images of 3I Atlas in September 2025. From that vantage point, the coma and tail were visible as a faint smear of light, stretching across the frame like a cosmic contrail. What makes all this remarkable is not just the variety of data, but the fact that we're getting it from multiple angles, across multiple wavelengths, from spacecraft that were never designed to coordinate on something like this. It's as if we accidentally built a distributed surveillance network without meaning to. Earth-based telescopes, Mars orbiters, deep space probes, all of them turning their eyes toward a single target and feeding data into a growing archive that, for the first time, gives us a three-dimensional, multispectral view of an interstellar visitor. This is unprecedented. When 1I Oumuamua zipped through in 2017, we barely got a few grainy images before it vanished. When 2I Borisov appeared in 2019, we had more time, but still only Earth-based telescopes to work with. 3I Atlas is different. We caught it from Mars. We caught it from deep space. We caught it in visible light and ultraviolet and infrared. But here's where the story takes a turn. Despite all this data, NASA didn't rush to release its findings. The images from the Mars Reconnaissance Orbiter didn't appear until weeks after the flyby. Officially, the delay was blamed on the United States government shutdown, which temporarily halted non-essential operations across federal agencies. Fair enough, bureaucracy has a way of slowing things down. But the timing felt strange. The European Space Agency had already published its own observations. The data was out there. The scientific community was buzzing. And yet NASA held back, as if waiting for something, waiting to verify, waiting to coordinate, or maybe just waiting to see how the public would react. When the images finally did appear, they were accompanied by careful, measured language. Officials emphasized that 3I Atlas posed no threat to Earth. They described it as a typical interstellar comet, following a predictable trajectory exhibiting normal outgassing behavior. Nothing to see here. Move along. But the contrast with Europe's approach was striking. Where NASA preached caution and patience, The European Space Agency moved with speed and confidence. They released data quickly. They framed the Mars flyby as a significant achievement. They didn't shy away from the implications, and in doing so, they sent a message. We are ready. We are capable. We are not waiting for anyone else to take the lead. So now we have the images. We have the data. We have multiple spacecraft confirming that 3I Atlas is real, that it's interstellar, that it's behaving more or less like a comet should behave. But we also have a gap, a delay, a moment of hesitation from the agency that usually dominates these stories. And that gap is where the speculation begins to grow. Because if the data is so straightforward, why the wait? If the object is so clearly a comet, why the careful language? And if this is just science as usual, why does it feel like something else is happening beneath the surface? From now on, we'll look at the science, but we'll also push the boundaries, examining what's known, what's hidden, and what might be deliberate. Because sometimes the most interesting part of a story isn't what's being said, it's what's being left unsaid. Part 3. Official Framing versus Alternative Interpretations. According to every official source you'll find, 3I Atlas is an interstellar comet, not a threat, not a mystery, just a chunk of ice and rock from another star system, passing through ours on a one-way trip back into the void. NASA's Planetary Defense Coordination Office has stated clearly that the comet will pass no closer than about 1.8 astronomical units from Earth. That's roughly 270 million kilometers. For perspective, Mars at its closest approach to Earth is about 55 million kilometers away. So 3I Atlas isn't even playing in the same league as a genuine impact threat. It's a spectator, not a participant. And the basis for calling it a comet is solid. Its orbital path is hyperbolic, meaning it came from outside the solar system and will leave again. That's the hallmark signature of an interstellar visitor. You can't fake hyperbolic trajectories. They're written into the mathematics of celestial mechanics. On top of that, the object behaves like a comet. It has a nucleus, a coma of gas and dust, a tail that points away from the sun. As it gets closer to our star, it heats up, volatiles sublimate, and material streams off into space. Classic comet behavior. The James Webb Space Telescope even captured infrared spectra of the coma, revealing that it's dominated by carbon dioxide, along with water vapor, carbon monoxide, a compound called OCS, plus dust and water ice. Now this is where things get interesting. Most solar system comets are water-rich. Carbon dioxide is present, but usually not the dominant component. But 3I Atlas is flipped. Its coma is loaded with carbon dioxide. That suggests it formed in a very different environment, possibly near the carbon dioxide ice line in its home protoplanetary disk, where conditions favoured carbon dioxide over water ice. So what does that tell us? It tells us that 3I Atlas is genuinely foreign. Not just foreign in the sense that it came from far away, but chemically and compositionally different from the comets we're used to. It's a sample from another stellar system, carrying clues about how planets and comets form around other stars. That's scientifically fascinating. It's also, from a certain perspective, deeply unsettling. Because if comets from other systems can have radically different compositions, then our assumptions about what interstellar objects should look like might be incomplete. We've been studying solar system comets for centuries. We think we understand them. But 3I Atlas is a reminder that the universe doesn't care about our models. It'll throw curveballs at us whenever it feels like it. And that's where the alternative interpretations creep in. Some researchers and commentators have pointed out that the images released so far are, to put it generously, not exactly high definition. The fuzzy white blob captured by the Mars Reconnaissance Orbiter doesn't resolve fine details. You can't see the nucleus clearly. You can't make out jets or surface features. It's a smear of light. And while that's understandable, given the distances and the limitations of the camera, it also leaves room for doubt. One well-known astrophysicist recently argued that we shouldn't judge a book by its cover, that the images are too blurry and inconclusive to definitively categorize the object's nature. He didn't say it's artificial, but he didn't rule it out either. And in the current climate, where interstellar objects are rare and every new discovery gets scrutinized to death, even a hint of ambiguity is enough to spark wild speculation. Then there are the polarization measurements. Recent observations show that 3I Atlas has an unusually strong negative polarization signal. Polarization refers to the orientation of light waves, and when light scatters off dust particles, it becomes polarized in predictable ways. But 3i Atlas shows a deeper, narrower negative polarization branch than anything previously seen in comets or asteroids. That could mean the dust is unusual. Maybe the particles are a different shape, or made of different materials, or coated with something we don't recognize. Or it could mean nothing. It could be an artifact of the observation, or a quirk of the comet's activity, or just another reminder that interstellar objects don't have to play by our rules. But here's the thing. When you combine the unusual composition, the odd polarization, the delayed data release, and the fact that Europe acted with such speed and confidence, you start to get a picture that's more complicated than comet equals boring. You get a picture where institutional behavior matters as much as the science, where what agencies choose to emphasize or downplay tells its own story, and where the line between scientific caution and strategic ambiguity starts to blur. No credible peer-reviewed evidence suggests 3i Atlas is artificial. None. But the absence of evidence isn't always evidence of absence. And in a world where the first interstellar object, 1I Oumuamua, sparked serious academic debate about whether it might be a probe, it's not surprising that people are asking questions. The viewer is left at a crossroads. Official calm versus public speculation. Which narrative do we trust? And what if the truth lies somewhere in between? Part 4. Claim laid out. Europe's unilateral planetary defense drill. Let's be clear about what the word unilateral means in this context. It doesn't mean Europe acted in secret or defiance of international law. It means the European Space Agency decided, independently, to use its Mars orbiters to track and image 3i Atlas without waiting for coordination or leadership from NASA. That might sound like a subtle distinction, but in the world of space agencies, where collaboration is the norm and joint missions are carefully negotiated years in advance, it's a significant move. Europe saw an opportunity. They took it. They didn't ask permission. They didn't wait for a committee to approve. They just did it. And in doing so, they demonstrated something that has enormous implications for the future of planetary defense. They proved that a non-Earth vantage point can be used to monitor interstellar objects. Mars orbit isn't just a platform for studying Mars anymore. It's a surveillance post, a watchtower looking outward into the solar system and beyond. This is the first time anything like this has been done. Previous interstellar visitors were tracked exclusively from Earth-based telescopes. We've never had the chance, or the foresight, to use planetary orbiters for this purpose, but 3i Atlas changed that. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express, both originally designed to study the Martian atmosphere and surface, were repurposed on the fly to point outward and capture images of a faint, fast-moving comet. That required precise timing, long exposures, careful image stacking, and the kind of operational flexibility that most space missions don't have. But they pulled it off, and in doing so, they effectively ran a planetary defense drill. Not officially, not with fanfare, but functionally, that's what it was. Think about what was tested here. Long-range detection from a planetary orbit, cross-planetary coordination between multiple spacecraft, multispectral analysis combining visible, ultraviolet, and infrared data, trajectory refinement as new observations came in, data-sharing protocols between agencies and international partners. All of these are capabilities you'd need if a real hazardous object were inbound. You'd need to detect it early. You'd need to track it accurately. You'd need to analyze its composition to understand whether it's solid rock, loose rubble, or volatile ice. You'd need to share that information globally so that governments and defense agencies could make informed decisions. And you'd need to do all of this under time pressure, with limited resources, using infrastructure that wasn't originally designed for defense. 3i Atlas gave Europe a chance to test all of that, and they passed. They detected the object, they imaged it from Mars orbit, they shared the data publicly, they demonstrated autonomy and readiness, and they did it while NASA was still sorting out its internal protocols and dealing with bureaucratic delays. Now, it's worth noting that NASA eventually released its own images and data. The Mars Reconnaissance Orbiter's close-up shot of the comet is arguably the best single image we have, but the delay mattered. In the court of public opinion, Europe moved first. Europe looked decisive. Europe looked prepared. And that sends a message, not just to NASA, but to every other spacefaring nation watching. If you want to lead in planetary defense, you need capability, speed, and the willingness to act independently when necessary. The political and policy dimension here is impossible to ignore. Space is no longer just about science, it's about strategy. It's about demonstrating technological prowess. It's about showing that you have the infrastructure and the will to respond to threats, whether those threats are terrestrial or cosmic. And when one of the world's major space agencies takes unilateral action, even if that action is framed as scientific observation, it has ripple effects. Other nations start to wonder, should we be doing the same? Do we have the capability? What if the next interstellar object is dangerous and we're caught flat-footed? These are the kinds of questions that drive policy. They drive funding. They drive the slow transformation of space agencies from explorers into sentinels. And here's the kicker. If this becomes the norm, if every major space agency starts treating interstellar objects as potential defense scenarios, then we're entering a new era. An era where the line between science and defense blurs, where every comet becomes a drill, where every anomaly triggers alarm bells. That might sound paranoid, but consider the alternative. Doing nothing, waiting until a real threat appears. And then discovering we don't have the protocols, the infrastructure, or the coordination to respond in time. Europe just fired the starting gun. Now the question becomes, who presses record first when the next interstellar visitor shows up? And what happens when the stakes are higher? Part 5. Questions raised. What's real? What's speculation? Despite all the excitement, all the data, all the imagery streaming in from spacecraft across the solar system, there's still a fog of ambiguity hanging over 3i Atlas. We know it's real. We know it's interstellar. We know it's behaving mostly like a comet. But mostly isn't the same as entirely. And that gap between mostly and entirely is where speculation thrives. So let's be honest about what we don't know and why it matters. The first core question is whether Europe's action was genuinely a planetary defense drill or just a high-profile, opportunistic scientific observation that's being dressed up with defense-style rhetoric after the fact. Because calling something a defense drill implies intent. It implies planning. It implies that the decision to track 3i Atlas from Mars orbit was motivated, at least in part, by strategic considerations rather than pure scientific curiosity. But where's the evidence for that? Well, there isn't any. Not publicly. No one from the European Space Agency has stood up and said, "We treated this as a defense exercise." No official statements describe it in those terms. The language used in press releases and scientific papers is careful, neutral, focused on the science. So why are some observers interpreting it as a drill? Because actions speak louder than words. The speed of the response, the coordination across multiple spacecraft, the public release of data, the unilateral decision-making, all of that looks more like a strategic move than a passive observation. It looks like Europe was proving a point, demonstrating capability, showing that they're ready. But proving a point isn't the same as conducting a drill, and demonstrating capability isn't the same as rehearsing response protocols. A real drill would involve more than just observation. It would involve tracking, analysis, simulation of response protocols, sharing data with defense infrastructure or alert networks, maybe even coordination with military or civil defense agencies. None of that has been publicly confirmed, so we're left in a grey zone. Did Europe treat this as a defense test? Or are we reading too much into their actions because we're primed to see threats and competition everywhere we look? It's hard to say, and that ambiguity is part of the problem. When agencies act in ways that can be interpreted multiple ways, it creates uncertainty, and uncertainty breeds speculation. Then there's the question of NASA's delay. Why did it take so long for the American side to release its Mars reconnaissance orbiter images? The official explanation is the United States government shutdown, which temporarily halted non-essential operations. That's plausible. Bureaucracy has a way of gumming up the works, but it's also convenient, because government shutdowns are a known problem. Space agencies plan around them. They prioritize critical operations. They have contingency protocols. So why didn't planetary defense observation count as critical? Or if it did, why weren't the images released sooner? Alternative explanations range from the mundane to the conspiratorial. Maybe the data was complex and required careful validation before release. Maybe there was internal disagreement over how to interpret anomalies in the images. Maybe NASA wanted to coordinate with international partners, and that took time. Or maybe there was a strategic decision to let Europe take the lead and see how the public reacted before committing to a narrative. We don't know. And that's the point. When institutions delay or withhold information, even for good reasons, it creates a vacuum. And vacuums get filled with speculation, sometimes justified, sometimes not. but always persistent. And then there's the image itself, the fuzzy white blob from the Mars Reconnaissance Orbiter. Is that compelling evidence for a comet? Or is it ambiguous enough to feed speculation? The truth is, it's both. To a trained astronomer, it looks like a comet. The coma, the tail, the diffuse cloud of gas and dust, all consistent with what you'd expect. But to someone less familiar with how faint objects appear in space imagery, it might look like nothing, a smear, a glitch, an artifact. And in the age of high-definition everything, where we're used to seeing Saturn's rings in crystal-clear detail and Martian landscapes that look like Earth deserts, a blurry blob feels disappointing. It feels incomplete. And incomplete evidence is the perfect breeding ground for doubt. Comets, especially faint interstellar ones, are notoriously difficult to image. The nucleus is small, the coma is dim, the background is full of noise, camera limitations, exposure times, spacecraft jitter, all of these can distort observations. So we should be cautious about overinterpreting what we see. But we should also be cautious about dismissing legitimate questions. Just because something looks like a comet doesn't mean it's only a comet. Just because agencies say it's safe doesn't mean there aren't anomalies worth investigating. And just because the official narrative is calm doesn't mean there isn't a deeper story lurking beneath the surface. We've laid the foundation. Now we dig deeper. Into technical details, anomalies, controversies, and speculative possibilities. Part 6. Technical depth. How ESA Mars orbiters. Let's talk about the machinery behind the magic. The European Space Agency's Mars orbiters weren't sitting around waiting for an interstellar comet to show up. They have day jobs. The ExoMars Trace Gas Orbiter spends its time studying the Martian atmosphere, hunting for methane and other trace gases that might hint at geological or even biological activity. Mars Express, the older sibling, maps the surface, studies the ionosphere, and relays data from rovers. These are planetary science missions. They point down at Mars, not up at the stars. So when 3i Atlas came screaming through the inner solar system, the decision to repurpose these spacecraft was anything but routine. It required operational gymnastics, planning, coordination, and a willingness to sacrifice Mars observation time for something that might not even produce good images. But they did it anyway. During the comet's close approach to Mars in early October 2025, both orbiters were commanded to turn away from their primary targets and point outward into deep space. They tracked the comet as it moved against the background stars, capturing long exposure images that had to be stacked and processed to bring out the faint signal buried in noise. This isn't trivial. 3i Atlas is dim, really dim. Compared to the bright Martian surface these cameras are used to imaging, it's like trying to photograph a firefly from 100 kilometers away. The signal-to-noise ratio is terrible. You need long exposures. You need multiple frames to stack together so random noise averages out and the real signal strengthens. You need precise pointing so the comet doesn't drift out of frame during the exposure, and you need post-processing algorithms that can distinguish between cosmic rays, hot pixels, background stars, and the actual comet. The fact that this worked at all is a testament to the flexibility and capability of these missions, but it's also a testament to the people running them, the mission planners who had to rewrite observation schedules on the fly, the engineers who had to calculate pointing angles and exposure times, the data analysts who had to sift through terabytes of raw imagery looking for a faint smudge that might or might not be there. This is the unglamorous side of space exploration, the part where success depends on spreadsheets and late-night troubleshooting sessions and hoping the software doesn't crash at the critical moment. And it wasn't just Europe. NASA's Mars Reconnaissance Orbiter joined the hunt, capturing what's arguably the best single image we have of 3i Atlas. The Perseverance rover on the Martian surface even got in on the action, imaging the comet from the ground. Multiple vantage points, multiple instruments, multiple wavelengths. This is redundancy in action. If one spacecraft fails, another picks up the slack. If one dataset is ambiguous, you cross-check against the others, and if everyone sees the same thing, then you can be more confident it's real, and not just an artifact or a glitch. The multi-wavelength aspect is especially important. Visible light imaging gives you the overall shape and structure. Ultraviolet observations, like those from the MAVEN orbiter, reveal gas emissions. Hydrogen glowing in ultraviolet wavelengths tells you water vapor is sublimating. Infrared spectroscopy, courtesy of the James Webb Space Telescope from Earth orbit, breaks down the chemical composition of the coma. Each wavelength tells a different part of the story, and when you combine them, you get a much richer, more complete picture than any single observation could provide. What does this technical success imply for the future of planetary defense? It means we already have the infrastructure. We don't need to build dedicated defense satellites or launch expensive new missions. We just need to be willing to repurpose what we already have. Planetary orbiters, heliophysics probes, solar observatories, even rovers on distant worlds. All of these can contribute to a distributed surveillance network, a web of eyes scattered across the solar system, all feeding data into a central analysis hub. That's not science fiction. That's what we just did with 3i Atlas, accidentally, without planning. Imagine what we could do if we planned for it. If we designed future missions with dual use in mind: science and defense, exploration and vigilance. We're already halfway there. The question is whether we're willing to take the next step. Part 7. Orbit, Trajectory and the Interstellar Visitor Background. 3i Atlas didn't just wander into our neighbourhood by accident. Well, actually, it did. But the point is, we caught it. The comet was first spotted on July 1st, 2025 by the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. That's a NASA-funded network of telescopes in Chile, designed to scan the sky for near-Earth objects that might pose a collision risk. It's a survey system, wide field, automated, constantly watching. And on that particular night in early July, it flagged a faint moving object that didn't match anything in the catalogue. Follow-up observations confirmed the suspicions. This wasn't a solar system native. Its orbit was hyperbolic. That means when you trace its path backward through time, it doesn't loop around the sun in a closed ellipse like planets and asteroids do. It comes from far away, swings past the sun in a sharp curve, and then heads back out into interstellar space. One and done. No return trip. Hyperbolic trajectories are the smoking gun for interstellar origin. You can't fake them. The math doesn't lie. When astronomers calculated the orbital elements of 3i Atlas, they found an eccentricity greater than 1. Eccentricity is a measure of how stretched out an orbit is. 0 is a perfect circle. Values between 0 and 1 are ellipses. 1 is a parabola. Anything greater than 1 is a hyperbola. And 3i Atlas clocked in well above 1. That's the signature of an unbound orbit, an object moving fast enough to escape the sun's gravity well and keep going forever. Unless, of course, something changes. A close encounter with a planet could alter its trajectory. Outgassing from the comet's nucleus could act like a tiny rocket, nudging it off course. But barring dramatic surprises, 3i Atlas is on a one-way trip out of the solar system. The perihelion, the point of closest approach to the sun, was around October 30th, 2025. At that moment, the comet was about 1.4 astronomical units from the sun. That's just inside Mars's orbit. Close enough to warm up and start outgassing, but not so close that it would cook and disintegrate like some comets do when they dive too near the sun. And here's the thing about hyperbolic trajectories and high velocities. They're dangerous. Not because 3i Atlas is dangerous. It's not. It's passing harmlessly through the solar system. But because the next interstellar object might not be harmless. And if it's moving at tens of kilometers per second on a hyperbolic path, we won't have much time to react. Weeks, maybe. Days if we're unlucky. That's the nightmare scenario planetary defense experts worry about. An object that appears out of nowhere, moving too fast to intercept or deflect, on a collision course with Earth. 3i Atlas is a preview of that scenario, a wake-up call. Because unlike the comets and asteroids we've been tracking for decades, interstellar objects don't follow predictable patterns. They don't come from the asteroid belt or the Kuiper belt or any other region we can monitor continuously. They come from the void, from directions we're not watching, at speeds we're not prepared for. And that makes detection incredibly hard. You need all sky surveys running constantly. You need automated systems that can flag unusual motion. You need follow-up telescopes that can confirm discoveries within hours. And you need a global coordination network that can mobilize quickly when something worrying appears. We have pieces of that system, but we don't have all of it. Not yet. And here's the rarity factor. 3i Atlas is only the third confirmed interstellar object ever detected. The first was 1i Oumuamua in 2017. The second was 2i Borisov in 2019. That's 3 objects in 8 years. Now that doesn't mean interstellar visitors are rare. It means our detection capabilities are still catching up. As survey telescopes get better, as automation improves, as we dedicate more resources to sky surveys, we're going to find more, maybe a lot more. Some estimates suggest there could be thousands of interstellar objects passing through the inner solar system at any given time, most of them too small or too faint to detect. But they're out there, and every once in a while one of them gets big enough, close enough, and lucky enough to be spotted. That raises the deep time angle. 3i Atlas is carrying primordial material from another star system. Ices that condensed billions of years ago in a protoplanetary disk around a star we'll probably never identify. Dust grains that witnessed the birth of alien worlds. This is a cosmic sample, a messenger from a place we can't visit and a time we can't revisit. And if we fail to study it now, during this brief window when it's close enough to observe, we lose that data point forever. The comet will leave, it'll vanish into the void, and we'll be left wondering what we missed. That's why planetary defense isn't just about protection, it's also about opportunity. Every interstellar object is a chance to learn something new. But only if we're watching, only if we're ready, and only if we have the tools and the will to seize the moment when it arrives. Part 8. Scientific Findings, Composition, Physical Properties, and Oddities. Let's talk about what 3i Atlas is made of, because this is where things get genuinely weird. The global observation campaign that tracked the comet involved everything from ground-based telescopes to space observatories to planetary orbiters. And when you combine all that data, you get a picture of an object that's both familiar and alien at the same time. The James Webb Space Telescope captured infrared spectra of the comet's coma, and what it found was striking. Carbon dioxide dominates the mix. Not water, not carbon monoxide, carbon dioxide. Now, that might not sound strange until you realise that most solar system comets are water-rich. Water ice is the primary volatile. Carbon dioxide is present, sure, but usually as a minor component. 3i Atlas flips that script. Its coma is loaded with carbon dioxide, along with water vapour, carbon monoxide, a molecule called carbonyl sulfide, dust particles, and water ice. It's a cocktail we don't normally see. So what does a carbon dioxide-dominated coma tell us? It suggests that 3i Atlas formed in a region of its home protoplanetary disk where carbon dioxide was more abundant than water ice. Maybe it formed farther out, where temperatures were just right for carbon dioxide to condense but too warm for water ice. Or maybe the thermal or radiation history of its parent system was different from ours. Either way, it's a clue that this comet comes from an environment that doesn't match the solar system's. It's genuinely foreign, chemically distinct, a sample from a different recipe. The size of the nucleus is still uncertain. Observations from the Hubble Space Telescope in July 2025 estimated the diameter somewhere between 440 metres and 5.6 kilometres. That's a huge range. The uncertainty comes from not knowing the albedo, the reflectivity of the surface. A dark low albedo object would need to be larger to reflect the same amount of light as a bright high albedo object. So until we can measure the albedo directly, we're stuck with error bars that span more than an order of magnitude. But even the small end of that range is substantial. 440 metres is bigger than most near-Earth asteroids we worry about, and 5.6 kilometres would make it a genuine giant, comparable to some of the largest comets in the solar system. Then there's the dust production. Photometric observations from July through September 2025 tracked how much dust the comet was, ejecting as it approached the Sun. The data shows a power law relationship. Dust production scaled with heliocentric distance to the negative 1.8 or negative 2 power. That's consistent with volatile-driven activity. As the comet gets closer to the Sun, it warms up, ices sublimate, and the gas carries dust particles off the surface. The specific exponent suggests that carbon dioxide sublimation is the primary driver. Water ice sublimates more slowly at the same temperatures, so if water were dominant, you'd expect a different exponent. But the numbers line up with carbon dioxide. More evidence that this comet is fundamentally different from what we're used to. Morphologically, the comet's appearance changed over time. Early observations showed a sun-facing dust fan, a feature common in active comets, where jets of gas and dust shoot out preferentially toward the Sun. Later, as the comet continued its approach, that fan evolved into a more traditional tail pointing away from the Sun. Solar radiation pressure was pushing the dust particles backward, shaping the tail into the classic teardrop structure we associate with comets. But here's the interesting part. The tail was dominated by larger, slower moving dust grains. Smaller particles, which are more easily pushed by radiation pressure, seem to be depleted. That could mean the comet's activity preferentially ejects large grains, or it could mean the small grains are composed of something that sublimates or disintegrates quickly. Or it could be an observational artifact. We don't know yet. And then there's the polarization data. This is where things get really strange. Polarimetry measures how light waves are oriented after scattering off particles. When sunlight hits dust in the comet's coma, some of it scatters toward Earth, and that scattered light becomes polarized. The degree and direction of polarization depend on the size, shape, and composition of the dust particles. Most comets and asteroids show a characteristic polarization curve. Positive polarization at large phase angles, negative polarization at small phase angles. The negative branch typically reaches a minimum of about 1%, but 3i Atlas shows a minimum of negative 2.7%. That's nearly 3 times deeper than normal, and the shape of the curve is narrower, more sharply peaked. This has never been seen before in a comet or asteroid. It suggests the dust particles have unusual properties. Maybe they're unusually fluffy or porous. Maybe they're coated with something exotic. Maybe their size distribution is skewed. We don't have a definitive explanation yet, but it's another data point that sets 3i Atlas apart from the crowd. So where does that leave us? On one hand, the data strongly support the natural comet hypothesis. Volatiles, dust, outgassing, a coma and tail, all the classic signatures. On the other hand, the specific details are uncommon. Carbon dioxide dominated, composition, unusual polarization, dust dynamics that don't quite match the textbook. None of this proves the object is anything other than a comet, but it does leave a sliver of uncertainty, a crack in the consensus, and that's where speculation thrives. Because when the data doesn't perfectly match expectations, even for good reasons, people start to wonder if there's more to the story. Part 9. Controversies and Alternative Theories. From Scientific Skepticism to Bold Hypotheses. The official consensus is clear. 3i Atlas is a natural interstellar comet. The evidence supports that conclusion. The orbital mechanics, the outgassing, the spectral data. All of it points to a chunk of ice and rock from another star system, behaving more or less as comets are supposed to behave. But consensus doesn't mean unanimity, and in the fractured, hyper-connected landscape of modern discourse, where social media amplifies dissent and skepticism spreads faster than peer-reviewed papers, alternative theories are bubbling up. Some are scientifically grounded, rooted in genuine questions about the data. Others are speculative, bordering on conspiratorial, and a few are outright wild. But they all share a common thread: the belief that the official narrative is incomplete, that there's more to 3i Atlas than we're being told. One of the loudest skeptical voices came from a well-known astrophysicist who recently argued that the images released by NASA and the European Space Agency are too blurry and inconclusive to definitively categorize the object. He didn't claim it's artificial, but he did say we shouldn't judge a book by its cover, that we need more data before ruling out non-natural origins. And in the current climate, where the memory of One-Eye Oumuamua and its bizarre tumbling motion and lack of a visible coma still lingers, that kind of statement carries weight. Because Oumuamua sparked genuine academic debate. Papers were published arguing it might be a light sail or a probe. Other papers pushed back, offering natural explanations. The controversy never fully resolved. It just faded as the object left the solar system and became too faint to observe. Now we're in round 2. And the skeptics are pointing to specific anomalies. The unusual polarization signal is Exhibit A, a negative polarization branch nearly 3 times deeper than normal, has never been seen before. That's not disputed. It's in the data. The question is what it means. Natural explanations exist: unusual dust composition, exotic grain structure, a size distribution skewed toward large, fluffy aggregates. But none of these explanations are definitive. They're plausible. They're consistent with the data, but they're not proven. And in the absence of proof, speculation fills the void. Some independent commentators have gone further, proposing that 3i Atlas could be artificial. A probe, a craft, a surveillance device sent by an advanced civilization to study our solar system, They point to its interstellar origin, its strange composition, the fact that it was observed from multiple angles by multiple spacecraft. They argue that the carbon dioxide-rich coma could be engineered. Maybe it's a propulsion system. Maybe it's a cloaking mechanism. Maybe it's unrelated to the object's true nature, a shell around something else. These are bold claims, and to be clear, they're not accepted by mainstream science. There's no peer-reviewed evidence supporting the artificial hypothesis, but they're out there, circulating, being discussed. And in an era where unverified claims can go viral before fact-checkers even finish their coffee, that matters. So let's lay out the counter-arguments. First, natural explanations exist for every anomaly observed so far. Carbon dioxide-rich comets are rare, but not impossible. Unusual polarization can be explained by exotic dust without invoking non-natural origins. The blurry images are exactly what you'd expect given the distances, the camera limitations, and the faintness of the object. Second, the burden of proof for artificial origin is extraordinarily high. You'd need to show features that can't be explained by natural processes, geometric structures, artificial signatures in the spectrum, acceleration that doesn't match outgassing. So far, none of that has been observed. Third, interstellar probes, if they exist, would likely be much smaller and harder to detect than 3i Atlas. Why send a giant kilometers-wide object when a tiny, stealthy probe would do the job better? But here's the risk. In a climate where fear of cosmic threats is rising, where planetary defense is becoming a policy priority, and where agencies are treating interstellar objects with unprecedented seriousness, faint anomalies can be amplified into dramatic narratives, speculation can morph into conspiracy, and public understanding can become distorted. That's dangerous. Not because speculation is inherently bad, but because it can undermine trust in institutions and make it harder to have rational conversations about real risks. There's a historical precedent here. When 1i Oumuamua appeared, the speculation was intense. Was it a comet, an asteroid, a light sail? The debate raged in academic journals and tabloid headlines alike. Eventually the consensus settled on a natural origin, though some questions remain unresolved. The lesson from Oumuamua is that fear and imagination fill gaps when data is limited. And 3i Atlas, with its blurry images and unusual properties, is ripe for the same treatment. The political dimension complicates things further. If agencies start treating every interstellar object as a potential threat, even for good reasons, it can influence policy and public perception in unpredictable ways. It can lead to overreaction, militarization, secrecy, or it can lead to the opposite: complacency, dismissiveness, a failure to take real risks seriously because we're desensitized by false alarms. As content creators, as journalists, as anyone engaging with this story, there's a responsibility to label speculation clearly, to differentiate between verified facts and hypotheses, to avoid sensationalism while still acknowledging genuine uncertainties. Because the truth is, we don't have all the answers yet. We know 3i Atlas is interstellar, we know it behaves like a comet, but we also know it's unusual. And unusual isn't the same as inexplicable. Sometimes a cigar is just a cigar, sometimes a comet is just a comet, and sometimes the most interesting part of the story is how we react to uncertainty. Part 10. Geopolitics. What yeses move signals and potential long-term implications. Space is no longer a neutral frontier where nations collaborate purely in the spirit of discovery, setting aside their terrestrial rivalries. That romantic vision, if it ever truly existed, is dead. In the 2020s, space has become a strategic territory, a domain where resources, surveillance, prestige, and defense are all intertwined. The stakes are no longer abstract or symbolic. They're concrete. And when the European Space Agency made the decision to track and image 3i Atlas from Mars orbit, they weren't simply performing a routine scientific observation. They were sending a message. Europe has capability. Europe has autonomy. And Europe is no longer willing to wait for American leadership to dictate the terms of engagement in space. That's the subtext, the unspoken message encoded in ESA's swift action and the public release of their data. It's a signal other spacefaring powers are watching closely. For decades, the United States has dominated space exploration. Since the Apollo era, NASA has commanded the largest budget, the most ambitious missions and partnerships that shaped the rules of the game. Its missions set scientific agendas, Its telescopes and orbiters defined what discoveries were possible, and its policies influenced how nations coordinated in space. But that dominance is eroding. China is building its own modular space station, landing rovers on Mars, planning lunar bases, and conducting ambitious deep space missions. India is accomplishing remarkable interplanetary work on modest budgets, demonstrating precision engineering and scientific innovation. Private companies, SpaceX, Blue Origin, Rocket Lab, and others, are deploying satellite constellations, building reusable rockets, and creating rapid response capabilities that were unimaginable a decade ago. And Europe, with its network of planetary orbiters, deep space probes, and Earth-observing satellites, is carving out a niche that is no longer just complementary, it's strategic. 3i Atlas offered Europe a chance to demonstrate this capability on the global stage by repurposing Mars orbiters to track the interstellar object, rapidly releasing imagery and trajectory data and framing the observation as a significant milestone in planetary defense. ESA made a deliberate statement. Europe can act independently. They didn't wait for NASA coordination or global consensus. They acted first and publicly. That act of decisiveness is a signal not only to the scientific community, but to policymakers and rival space agencies. Europe is asserting itself in the emerging planetary defense arena. Other nations are undoubtedly taking note. If Europe can adapt planetary orbiters for surveillance and early warning, what's stopping China from doing the same? Or India? Or Russia? What's preventing private corporations from offering early warning services to governments or even to paying customers? The reality is, nothing. There are currently no treaties or international frameworks that clearly define who monitors, who analyzes, or who races alerts regarding interstellar objects or other potential cosmic hazards. We exist in a policy vacuum, and vacuums are quickly filled, often unpredictably and sometimes dangerously. This vacuum could fuel a new kind of space race, not one focused on reaching the Moon or Mars first, but on building the most comprehensive planetary defense and early warning networks. A race to demonstrate technological capability, to be the first to detect and track the next interstellar visitor, and to provide reliable data that can guide mitigation decisions. Unlike the Cold War space race, which was largely about prestige and ideology, this competition has very practical stakes. The next interstellar object might not be benign, it could be hazardous. Whoever detects it first, who provides the most accurate trajectory predictions, and who offers the most actionable data, will wield influence over both public perception and international response. That is power, strategic power, in a domain that has historically been considered neutral. Yet competition isn't the only possible outcome. Planetary defense is inherently a global concern. An object on a collision course with Earth doesn't respect borders. Its threat is universal. This creates a strong incentive for cooperation. Agencies could share data, coordinate observations, and jointly develop response strategies. But the tension between national pride, strategic advantage, and collective responsibility is palpable. ESA's move could be seen in two ways: as a unilateral flex, demonstrating capability while bypassing collaborative norms, or as a proactive demonstration designed to motivate other agencies to participate in a coordinated effort. Which interpretation dominates could shape the trajectory of planetary defense policy for decades. The questions facing NASA and other agencies are complex. Will NASA respond by embracing transparency and collaborative approaches, or will it treat planetary defense as a national security issue, hoarding data and limiting access? Will China and India participate in an international early warning network, or will they pursue parallel systems, keeping observations classified? These are not merely technical or operational questions. They are questions of strategy, diplomacy, and international norms. Cooperation makes sense scientifically and morally. Competition makes sense politically and strategically. In the absence of clear rules, nations tend to choose the path that maximizes their advantage. Economic factors further complicate the landscape. If planetary defense becomes a recognized policy priority, governments will inevitably invest in dual-use space assets. Telescopes and sensors capable of both science and surveillance, orbiters that can study planetary bodies while monitoring interstellar space, launch systems designed for rapid deployment or interception. A new industrial ecosystem will emerge. Defense contractors, private aerospace companies, data analytics firms, and startups, all vying for contracts and investment in a field where stakes are high and failures are costly. Space is no longer just a frontier of knowledge, it's a frontier of profit, where technological capability translates into political influence and economic opportunity. Ethical considerations are equally complex. What if an object of interest is misinterpreted? A benign comet could trigger a false alarm, causing unnecessary mobilization of resources, public panic, and diplomatic friction. Who decides what constitutes a credible threat? Who has the authority to declare an emergency? Who bears responsibility if decisions based on incomplete or uncertain data result in damage or loss of life? These are not hypothetical concerns. They are plausible scenarios that policy experts and risk analysts think about constantly. The consequences of overreacting or underreacting could be catastrophic. 3i Atlas may well be the spark that forces these difficult questions into the open. It could mark the moment when planetary defense becomes a mainstream policy concern, moving from the domain of astronomers and disaster planners into global security and governance discussions. It might catalyze investments, treaties, and frameworks that create lasting infrastructure for monitoring, tracking, and mitigating cosmic threats. Or it might fade from public memory, relegated to scientific papers and technical briefings, with policy responses delayed until the next object arrives, potentially one less benign than 3i Atlas. If we are to act responsibly, the transformation from passive observation to active vigilance is essential. The shift requires more than telescopes and spacecraft. It demands governance, clear protocols, international collaboration, and public communication strategies. It requires thinking in terms of readiness, not just exploration, in terms of defense, not just discovery. The tools and data exist to detect and track interstellar visitors, but infrastructure, funding, and policy frameworks lag behind. Without a proactive approach, humanity will always be reacting to cosmic surprises rather than anticipating them, and time is of the essence. The window to respond to interstellar visitors is inherently narrow. These objects move fast, often exceeding tens of kilometers per second. Detection, characterization, trajectory prediction, and mitigation planning must all happen on compressed timelines. If agencies hesitate, delay, or fail to coordinate, the margin for action shrinks and risks increase exponentially. Preparedness is not optional. It is the only rational approach to a threat that could, in theory, affect the entire planet. 3i Atlas, then, is not just a scientific curiosity. It is a test case for planetary defense policy, international cooperation, and strategic foresight. It highlights the shifting dynamics of space geopolitics, where capability, transparency, and speed are now as important as scientific acumen. Europe's decision to act decisively serves as a reminder that space is no longer a neutral arena. It is a contested domain where actions and inactions have consequences. The implications stretch far beyond a single interstellar comet. They touch on governance, ethics, economics, and security in a rapidly evolving space environment. In the end, the questions 3i Atlas raises are clear. Will nations embrace cooperation or competition? Will agencies invest in infrastructure, protocols, and early warning networks, or will they wait for a crisis to force their hand? Will the next visitor be benign, or will it be a wake-up call we're not ready for? The path forward is uncertain, but the opportunity is real. Planetary defense can no longer be a niche pursuit. It must become a central element of how humanity approaches space, a field where readiness, vigilance, and foresight are the measures of responsibility. 3i Atlas may be the spark that ignites this transformation, or it may fade into the background, another moment of scientific excitement soon overshadowed by the next discovery. The difference will depend not on the comet itself, but on us. The decisions we make, the investments we commit to, and the foresight we demonstrate in the face of an unpredictable universe. In the vast expanse of space, vigilance is our greatest defense, and the actions we take now will determine whether humanity is ready when the next interstellar visitor arrives. Part 11. Broader space surveillance potential. Solar and heliophysics missions join the watch. So let's talk about what we actually know now, stripped of speculation and theatre. 3i Atlas was real. That fact alone should give you pause. For decades, astronomers watched the sky with one eye open, cataloguing distant objects, tracking near-Earth asteroids, occasionally sending probes to knock rocks off course. But 3i Atlas changed the equation entirely. It came from outside, carried velocity we couldn't have predicted, and forced every space agency on Earth to wake up and recalibrate what planetary defense actually means when the threat doesn't follow the rules. We now have multi-vantage, multi-spectral data on an object that originated beyond our solar system. NASA's satellites caught it, ESA's instruments tracked it, Mars orbiters photographed it, solar and heliophysics missions recorded its interaction with the solar wind. Stereo. A spacecraft, positioned in an orbit trailing behind Earth, used its heliocentric imager to stack hundreds of frames and pick up the faint signal. SOHO, sitting at the Sun-Earth L1 Lagrange point since 1996, added its coronagraph data to the pile. Punch observed from over 350 million kilometers away. Parker Solar Probe, diving closer to the Sun than any human-made object in history, might have contributed readings we haven't even seen yet. That's not just a lucky break or a once-in-a-lifetime alignment of circumstances. That's infrastructure finally working the way it was designed to work. And the fact that it worked should terrify you just as much as it should comfort you, because it means we're now capable of seeing things we were blind to just 10 years ago. Which also means we're now aware of how many things we still can't see. The event itself was a scientific goldmine. Researchers gained real-world data on interstellar dust composition, magnetic field interactions, trajectory deviations caused by outgassing, and thermal signatures in near-planetary space. They got to test detection algorithms under actual threat conditions, not just in simulations. They learned which instruments were sensitive enough, which data pipelines were fast enough, and which coordination protocols actually functioned when pressure was applied. But it was also a wake-up call, because 3i Atlas didn't announce itself politely. It didn't send a postcard from the Urat cloud saying it was on its way. It just appeared, moving fast, already inside the decision window where any meaningful response would require luck, preparation, and speed. And we got lucky. It missed. It didn't fragment catastrophically near Mars. It didn't deviate into an Earth-crossing trajectory. It just flew past, left some blurry photographs and vanished back into the void. But luck is not a strategy, and counting on luck twice is negligence. Here's where things get uncomfortable. The anomalies in composition, polarization, and dust behavior haven't been fully explained. Scientists have theories, they have models, they have peer-reviewed papers arguing for natural processes that could account for the data. But those papers also include phrases like, further observation needed, and alternative interpretations cannot be ruled out. Which is academic speak for, we don't actually know yet. And that ambiguity leaves space for speculation, conspiracy, and all the wild theories that thrive in the gaps where certainty hasn't yet arrived. No verified evidence for artificiality exists, let me say that clearly. Nothing we've seen proves 3i Atlas was anything other than a comet with unusual properties. But not proven is not the same as impossible. And that distinction matters when you're talking about objects that come from places we've never been and may never reach. What 3i Atlas represents is a paradigm shift. We've moved from passive astronomy, where we wait for things to happen and then publish papers about them, to active awareness, where detection, tracking, and potential response are treated as operational necessities. That shift requires infrastructure. It requires funding. It requires new policies that cross national borders and institutional rivalries. And it requires political will, which is the hardest resource to generate because it demands that governments spend money on threats that might never materialize. But the alternative is waiting until something does materialize, and by then it's too late to build the satellites, train the teams, or coordinate the international response. Building a distributed cosmic early warning system isn't cheap, but it's a lot cheaper than excavating cities after an impact. We already have the bones of this system: planetary orbiters, solar observatories, heliophysics probes, telescopes on Earth and in orbit, all feeding data into a growing archive. The beauty of this mesh is its redundancy. If one spacecraft is pointed the wrong way, another might catch the target. If one dataset is ambiguous, you cross-check against others. If everyone sees the same thing, confidence goes up, and if someone sees something different, that's valuable too, because anomalies drive discovery. But building this mesh deliberately, rather than relying on happy accidents, would require coordination. Missions would need to share data in real time, or near real time, observation schedules would need to be flexible enough to pivot when a target of interest appears. Data formats would need to be standardized so analysis tools can ingest feeds from different sources, and some agency or consortium would need to serve as the coordination hub, the clearinghouse where observations flow in, get analyzed, and trigger alerts if something concerning is detected. So here's the question that keeps circling back. Will space agencies embrace a permanent interstellar object early warning system? Will they fund it properly, staff it seriously, and give it the authority to act without waiting for committees to debate terminology? Or will this moment fade, replaced by budget cuts and shifting priorities until the next object appears and we scramble all over again? And beyond infrastructure, there's the geopolitical dimension. Will international cooperation rise, driven by the shared recognition that no single nation can handle these threats alone? Or will competition and secrecy dominate, with countries hoarding data, protecting proprietary technology, and treating space defense as another arena for strategic advantage? Because if we can't cooperate on something as universally threatening as an interstellar impact, then we've already lost. ESA's unilateral move with 3i Atlas demonstrated that cooperation is optional, not guaranteed, and that should worry anyone paying attention. Public perception will shape all of this more than scientists want to admit. If governments classify too much, people will assume cover-ups. If they release raw data without context, people will misinterpret it. If they say nothing, people will fill the silence with fear. The balance between transparency and responsible communication is delicate, but it's not optional. Open data, multi-agency collaboration, and public communication should be prioritized, not as idealistic goals, but as practical necessities. Because paranoia spreads faster than asteroids, and misinformation can do just as much damage as an actual impact. You can't defend a planet if half the population thinks you're lying to them. And then there's the human dimension, which is easy to forget when you're talking about orbital mechanics and spectroscopy. Space is enormous, unpredictable, and fundamentally hostile to life. Objects move at velocities that turn physics into a weapon. Distances are so immense that light itself takes hours to cross them. And the universe doesn't care about our survival. It doesn't send warnings. It doesn't negotiate. But we are no longer helpless. Our growing ingenuity, our expanding network of sensors, our improving ability to model and predict, all of that can turn cosmic mystery into manageable risk. Not zero risk. Never zero. But manageable. Which is more than any previous generation could say. Our ancestors looked up at the sky and wondered. We look up and measure. That's progress, even if it comes with new anxieties. 3i Atlas was the demonstration project. Accidental or deliberate, it proved the viability of a distributed detection network. It showed that spacecraft scattered across the solar system, all designed for different purposes, can pivot and contribute when something unexpected appears. It showed that data sharing works, that multi-vantage observations provide clarity, and that real-time coordination is possible when the stakes are high enough. Now the question is whether we take the next step, whether we turn a lucky break into a permanent capability, whether we build the cosmic early alarm system that might one day save millions of lives, or whether we let the moment pass and hope we get lucky again next time. So whether 3i Atlas was a cosmic messenger, a comet, or simply a strange visitor from a place we'll never visit, it doesn't actually matter. What matters is what we choose to do next. Because in the dark between the stars, vigilance might be our greatest defense. Not weapons, not walls, just attention. Just the willingness to look up, stay curious, and refuse to pretend the universe is safer than it actually is. Stay curious, stay skeptical, and stay ready. Because if humanity wants to survive, not just on Earth, but as a species aware of the cosmos, this may be the moment we truly begin to listen. Part 12. Alternative threat scenarios. What if an interstellar object is dangerous? Modelling extreme cases. 3i Atlas passed through the inner solar system without incident. It posed no threat to Earth. From the perspective of physics and planetary defense, it behaved more or less like a comet should, a small icy body drifting in from the vastness of interstellar space, sublimating as it approached the sun, trailing dust and gas along predictable trajectories. Astronomers watched it with curiosity, collected valuable data, and then waved it goodbye as it continued its lonely journey back into the void. For humanity, it was a reminder of our ability to detect distant visitors, but not a reason for alarm. But what if the next interstellar visitor is different? What if the next object isn't a benign ice ball, drifting serenely through the solar system, but something hazardous? Something that could, in the worst-case scenario, kill millions if we're unprepared. That's the nightmare scenario planetary defense experts think about. Not because it is likely, interstellar visitors are rare, but because if it happens, the consequences are catastrophic. Catastrophe doesn't wait for probability, it only cares about magnitude. Let's walk through a hypothetical. Imagine a future interstellar object, roughly the same size and speed as 3I Atlas, detected inbound toward Earth. Initially, it looks like a typical comet, a fuzzy coma, a diffuse tail pointing away from the Sun. Ground-based telescopes report a harmless-looking trajectory. But as the data flows in and more powerful instruments like the James Webb Space Telescope or planetary orbiters begin to study it, anomalies appear. Spectroscopy reveals a composition that raises eyebrows. Not just water and carbon dioxide, but volatile chemicals that could be toxic if released into the atmosphere. Or perhaps the nucleus is structurally unstable, likely to fragment under solar heating, creating multiple smaller impactors instead of a single predictable object. Or maybe its trajectory is slightly off what was initially predicted, a small non-zero chance that it could intersect Earth's orbit during a future perihelion passage. Each small deviation in the trajectory or unexpected property compounds the risk. The hazards could take multiple forms. High-velocity impact is the obvious one. An interstellar object moves at tens of kilometers per second, much faster than any object bound to the solar system. Even a relatively small nucleus, a few hundred meters across, carries immense kinetic energy. A direct collision with Earth could release energy equivalent to hundreds of megatons of TNT. For perspective, the largest nuclear weapon ever detonated, the Tsar Bomba, was about 50 megatons. An interstellar impact of this scale wouldn't just level a city or a small country, it could devastate an entire continent, triggering tsunamis, fires, and a global climate disruption, akin to what may have killed the dinosaurs 66 million years ago. Fragmentation adds another layer of risk. Comets are loosely bound collections of ice, dust, and rock. If this hypothetical object were to break apart as it approached the Sun, it could scatter dozens or hundreds of smaller fragments across a wide swath of Earth's orbit. Instead of a single impact point, humanity could face multiple strikes spanning continents. Even fragments too small to obliterate entire cities could still destroy infrastructure, contaminate air and water, and induce widespread panic. Outgassing, the very process that gives comets their characteristic tails, creates yet another complication. Jets of gas escaping from the surface act like natural rocket engines, subtly but continuously nudging the object off course. For a comet moving hundreds of millions of kilometers through space, even tiny forces can accumulate into significant deviations from a purely Newtonian trajectory. That makes interception extraordinarily difficult. You can't simply aim where the object is, you must predict where it will be when your deflection or interception attempt arrives. And if the object is outgassing unpredictably, that prediction becomes a guessing game, subject to errors that could render even the most sophisticated planetary defense measures ineffective. Then there are the unknowns. What if the object is artificial? The idea may sound like science fiction, but planetary defense experts are trained to think about even low-probability scenarios because the stakes, human survival, demand it. What if the object contains radiation, exotic materials, or technology we don't understand? What if it is a probe or some other artifact from an advanced civilization, and any attempt to intercept or study it is misinterpreted as hostile? These possibilities are admittedly remote, but the consequences of miscalculation would be immense. In risk assessment, low probability doesn't excuse inaction when the potential loss is extinction level. So let's use 3I Atlas as a template and imagine a response timeline for such a scenario. Detection happens first. A wide-field survey telescope flags an unusual object moving against the background of stars. Follow-up observations, perhaps using higher-resolution instruments, confirm that it is interstellar and potentially hazardous. That data flows into a coordination hub, whether it be NASA's Planetary Defense Coordination Office, a European equivalent, or an international consortium designed for global alerts. Governments are notified. The public is informed carefully, with messaging designed to avoid panic while emphasizing the need for vigilance. Next comes characterization. Scientists determine the object's composition using spectroscopy, analyze its brightness and reflectivity with photometry to estimate size, and model its trajectory with high-precision astrometry. Multiple platforms contribute data: planetary orbiters, solar observatories, radar, and ground-based telescopes. All of this feeds into increasingly refined models to predict the object's path, its potential for fragmentation, and the effects of outgassing. Understanding these factors in real time is essential for deciding whether mitigation is even feasible. If the object is confirmed as a threat, mitigation options are evaluated. One possibility is a kinetic impactor. A spacecraft rams into the object at high speed, imparting enough momentum to alter its trajectory slightly. Even a minor deflection, measured in fractions of a milliradian, can make a huge difference if done far enough in advance. Another option is a gravity tractor. A spacecraft hovers near the object, using its own gravitational pull to gently tug the object onto a safer course over weeks or months. A nuclear device could also be considered, detonated near or on the object to vaporize part of its surface, generating a jet of gas to push it off course. Each of these approaches is theoretically possible, but none have ever been tested on an interstellar object traveling at hyperbolic speed, meaning the margin for error is significant. The challenges are immense. Interstellar objects move fast. Detection might occur too late for any mitigation to succeed. Launch windows for interceptors are narrow. Tumbling or outgassing can make targeting nearly impossible. Fragmentation could turn one threat into dozens or hundreds. And international coordination, always a challenge, becomes even more complex when the threat is cosmic, crossing national jurisdictions and requiring cooperation between multiple space agencies with different priorities, technologies, and political agendas. There's also the risk of false alarms. A benign comet could trigger worldwide panic if it is misinterpreted as a threat. Agencies would face pressure to act decisively, but acting too soon based on incomplete data could waste resources or cause diplomatic incidents. Once public trust is damaged, it is hard to rebuild, particularly when citizens are asked to follow instructions or accept costly mitigation programs in future scenarios. Communicating uncertainty, balancing transparency with responsibility, is a delicate, high-stakes task. So what's the answer? Prudence. We hope that 3i Atlas is representative, a rare, benign visitor that gives scientists a chance to practice detection, observation, and analysis without risk. But planetary defense experts plan as if the next object could be worse. That means building detection networks capable of identifying small, fast-moving objects from multiple vantage points. It means developing mitigation technologies and testing them on harmless targets to refine our methods. It means establishing international protocols for data sharing, decision-making, and rapid coordination in the event of an imminent threat. And it means clear, thoughtful public communication that builds trust rather than panic. Because the alternative, doing nothing and hoping for the best, is a gamble we might not survive. The universe is indifferent to our plans, our schedules, or our assumptions about safety. 3i Atlas passed safely, but next time we might not get such a generous visitor. An interstellar object could arrive on a collision course with no warning. Its composition could be exotic, its trajectory unpredictable, and its effects catastrophic. And when the margin for error is measured in hours and kilometers, hope alone is not enough. In short, planetary defense is not just about science, it's about preparedness, coordination, and imagination. We must imagine the worst, plan for it, and ensure that when the next 3i Atlas, or something far more dangerous, arrives, humanity is ready. That readiness requires vigilance in observation, rigor in modeling, innovation in mitigation, and above all, cooperation across borders and disciplines. 3i Atlas taught us the universe can send visitors from other stars. The real lesson is that we must never assume the next visitor will be harmless, because the universe doesn't care about our luck, and next time we might not get a warning. Part 13, New Frontier, AI, Big Data and Automated Early Warning Systems for Space Hazards. The volume of astronomical data being generated every day is staggering. Sky surveys capture millions of images, each containing countless stars, galaxies, and moving objects. Spacecraft transmit terabytes of telemetry, often in streams that are almost continuous. Observatories around the world, from professional research facilities to automated backyard telescopes, scan the skies every night, flagging moving objects, transient events, and anomalies. And the rate of data production is accelerating. New missions are launching with increasing frequency. Telescopes are growing larger, their sensors higher in resolution, capable of capturing fainter and more distant objects than ever before. Every new instrument adds to the flood of information, producing far more data than human analysts could ever hope to process manually. That's where artificial intelligence comes in. Machine learning algorithms, programs designed to recognize patterns in vast datasets, offer a solution. They can sift through noise and highlight signals that matter, distinguishing between cosmic rays, asteroids, comets, satellites, and entirely unknown objects. They can flag unusual trajectories, unexpected accelerations, and anomalous spectral signatures. They do in seconds what would take human teams weeks, and they can operate continuously, without fatigue, bias, or distraction. Where humans are limited by attention span, scheduling, and the inevitable errors of manual work, AI operates relentlessly, scanning millions of data points with consistent rigor. 3i Atlas demonstrated the raw material that AI could work with. Multiple spacecraft captured images across multiple wavelengths. Ground-based telescopes provided follow-up observations. Spectroscopy revealed chemical composition. Photometry tracked brightness changes over time. All of that data exists in archives. It's accessible. But what's missing is the automated pipeline that could ingest it all, analyze it in real time, and raise alerts the moment something interesting or concerning appears. That pipeline is technically feasible. Machine learning models can be trained on historical data, known comets, asteroids, interstellar visitors, and anomalies. Once trained, these models can continuously scan new data streams, searching for outliers, objects that don't fit expected patterns that might be interstellar, hazardous, or both. The potential applications are enormous. Imagine an AI-powered cosmic hazard detector running 24/7, monitoring feeds from dozens of observatories and spacecraft simultaneously. An object enters the inner solar system. Within hours, the algorithm detects it. Its trajectory analysis identifies it as interstellar. Spectroscopy suggests a chemical composition worth flagging. Photometric analysis estimates size and activity levels. The system predicts the trajectory with high confidence, generating alerts that flow instantly to decision-makers, planetary defense offices, and even the public. All of this happens automatically. No need for a human to sift through millions of images manually. No delays while committees meet and debate. Fast, reliable detection and characterization could become routine. But challenges remain. Training AI models requires massive data sets. And we don't have many examples of interstellar objects, 3 confirmed, maybe a handful more that went undetected or unconfirmed. That's far too few to train a robust model capable of distinguishing subtle differences in trajectory, composition, or behavior. To compensate, researchers would need to create synthetic datasets. Simulations could generate artificial comets and asteroids with a wide range of properties, trajectories, compositions, and activity levels. Models could learn to recognize the signatures of interstellar objects even without having seen an exact match in real life. But simulations carry risk. They're only as accurate as the assumptions that underpin them. If the assumptions are wrong, the AI could fail to recognize a real threat, or flag harmless objects as dangerous. False alarms are another concern. Machine learning models make mistakes. They misclassify, see patterns where none exist, or overemphasize random fluctuations. If an AI system flags a benign object as hazardous and triggers a global alert, the consequences could be severe. Public panic, economic disruption, and loss of trust in space agencies and scientific authorities. This means any automated system must include safeguards, human oversight, validation protocols, and perhaps multiple independent confirmations before alerts are issued. These measures slow the process but dramatically reduce the risk of crying wolf. In a high-stakes scenario, careful verification is essential. There is also a dual-use problem. AI-powered detection systems can be used for peaceful science, tracking comets, asteroids, and other celestial phenomena, but they could also be militarized. Governments could use them to track adversaries' satellites, monitor space-based weapons, or gain strategic advantage over rivals. This is not paranoia. It's already happening. Space is already a theatre of surveillance and strategic competition. Introducing AI makes these systems faster, more accurate, and harder to counter, raising complex questions of governance and control. Who owns the data? Who decides what gets flagged as a threat? Who has access to alerts? And who ensures they are used responsibly? What happens if trust breaks down in an international crisis? These are serious questions for planetary defense and space security alike. Despite the challenges, the path forward is clear. Integrating AI detection modules into existing missions is essential. Funding research into robust, interpretable models that can explain their decisions is critical. We can't blindly trust a black box system when millions of lives could be at stake. Open-source early warning networks, where data is shared transparently, could help build trust, facilitate rapid follow-up observations, and allow scientists worldwide to collaborate. Protocols need to be established for what data is public versus restricted, and safeguards must prevent misuse. Human judgment remains central, but AI acts as a force multiplier, extending capabilities, accelerating analysis, and providing early warning for threats we might otherwise miss. By the 2030s, it is conceivable that we will have a global space situational awareness grid powered by AI. Nodes on Earth, Mars, and solar observatories scattered throughout the solar system could feed data into a distributed network, watching the skies constantly. The system would look for the next three-eye atlas, the next potential hazard, or the next mystery that challenges our understanding of physics and interstellar travel. When that moment comes, whether it's a harmless visitor or a true threat, we will be better prepared. AI could buy humanity the seconds, hours, or days needed to respond effectively. Consider the operational implications. Detection is only the first step. Once a potential threat is flagged, AI can immediately coordinate observations across multiple platforms, cross-check data, and refine trajectory predictions in near real time. Spectroscopy analysis can determine whether the object contains hazardous volatiles, unusual isotopes, or structural instabilities. Photometry can track rotation, shape, and brightness fluctuations. All of this happens faster than any human team could achieve manually. Decisions regarding planetary defense interventions, whether kinetic impactors, gravity tractors, or even nuclear deflection, can then be informed by AI-generated models, simulations, and probabilistic risk assessments. Humans still make the ultimate decisions, but AI provides the data, predictions, and analysis that allow those decisions to be timely and well-informed. Furthermore, AI could reveal patterns in astronomical data that humans might overlook. Tiny deviations in the motion of a comet, subtle spectral anomalies, or rare orbital configurations might hint at interstellar origin or unusual composition. Detecting these needles in a cosmic haystack is exactly what AI excels at. Over time, the system could even learn to predict where interstellar objects are most likely to appear, optimizing telescope scheduling and resource allocation. This predictive capability could transform planetary defense from reactive to proactive. The benefits extend beyond hazard detection. AI-enhanced surveillance could accelerate fundamental scientific discovery. Unknown asteroid families, transient phenomena, or exotic interstellar visitors could be catalogued systematically. Solar system dynamics, cometary physics, and exoplanetary science could all benefit from richer, faster, and more comprehensive datasets. But as always, this comes with responsibility. Ethical considerations, dual-use risks, and the need for transparent governance must guide development. Ultimately, relying solely on human analysts to manage exponentially growing astronomical data is unsustainable. The scale and complexity of the cosmos demand tools that can match it. AI is not a replacement for human judgment. It is a force multiplier, extending human capabilities, compressing timelines, and providing the vigilance necessary to safeguard our planet. Without it, the next three-eye atlas, or something far more hazardous, could arrive undetected, leaving humanity scrambling at a dangerous disadvantage. In the vastness of space, vigilance may be our greatest defense, and AI may be the only way we stay vigilant long enough to matter. By combining human judgment, advanced observational networks, and intelligent algorithms, we can transform planetary defense from reactive hope into proactive preparedness. The universe will continue to send visitors from the stars. Some will be harmless, some may not. Our ability to detect, analyze, and respond will define how well we survive the next cosmic surprise. Part 14. Historical Perspective and Comparable Precedents. Previous interstellar visitors and lessons learned. 3i Atlas is not humanity's first encounter with an interstellar visitor. Before it came, there was 1i Oumuamua in 2017 and 3i Borisov in 2019. These objects were the trailblazers, the first confirmed visitors from beyond our solar system. The lessons we learned from them, or failed to learn, shaped how we responded to 3i Atlas. They also serve as a stark reminder. Interstellar visitors are real, unpredictable, and rare, and every encounter is a fleeting opportunity to study the unknown. 1i Oumuamua was discovered by the Pan-STARRS telescope in Hawaii on October 19, 2017. At first, astronomers classified it as an asteroid or comet, a routine designation based on its appearance. But follow-up observations revealed something extraordinary. Its orbit was hyperbolic. Unlike the planets, asteroids, and comets that circle the Sun, Oumuamua was unbound. It wasn't a resident of our solar system, it was passing through, a traveller from the distant stars. When researchers traced its path backward, they found it came from the direction of the constellation Lyra. It was interstellar, the first confirmed visitor from another star system, and yet, Oumuamua was strange. Unlike a typical comet, it had no visible coma, no tail, and no obvious signs of outgassing. Comets usually brighten as they near the Sun, sublimating ice into vapour that forms a diffuse atmosphere and tail. Oumuamua remained stubbornly inert, even as it passed relatively close to the Sun, yet its trajectory revealed a slight, unexplained acceleration as it moved away. For comets, acceleration comes from outgassing. The jets of vapour act like tiny rockets, subtly pushing the object along its path. But for Oumuamua, there was no visible gas to explain the push. The scientific community proposed several hypotheses. Some suggested it had an unusual shape, maybe pancake-like or cigar-shaped, such that sunlight reflecting off its surface could provide enough radiation pressure to account for the acceleration. Others proposed far more provocative ideas. What if Oumuamua was artificial? A light sail? A probe sent intentionally by an advanced civilization to explore distant systems? A technological artifact gliding silently through the cosmos? This latter idea, championed by a prominent Harvard astrophysicist, made international headlines. While it was never widely accepted in mainstream astronomy, it opened a door to speculation. It forced us to consider that interstellar objects might not always be natural, that some could, in theory, be technological, and therefore carry entirely different risks and opportunities. 3i Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, was far less controversial. Unlike Oumuamua, Borisov behaved like a typical comet. It had a visible coma and a tail, outgassing as expected. Spectroscopic analysis revealed familiar chemical signatures: water vapour, cyanide, and dust consistent with solar system comets. In other words, Borisov was a normal comet, just with a trajectory that originated outside our solar system. Its composition and behaviour were predictable, and it presented no extraordinary anomalies. But Borisov demonstrated something crucial. Interstellar visitors are not only real, they are detectable. Our sky surveys are capable of finding them, and with careful, coordinated observation, we can track them, measure their properties, and learn from them. Unlike Oumuamua, Borisov allowed astronomers to practice multi-wavelength observation, spectroscopy, and trajectory modelling in a way that was more straightforward. Each successive interstellar visitor teaches us something new, refining the methods and technologies we use to understand these rare visitors. So what did we learn from these two objects? First, interstellar visitors exist. They are not hypothetical. Occasionally they pass through our solar system, a reminder that our neighbourhood is just a tiny bubble in a galaxy full of wanderers. Second, they are rare. Only 3 confirmed objects in 8 years, despite advanced surveys covering large portions of the sky. Third, detection requires vigilance. Automated sky surveys, rapid follow-up observations, and international coordination are essential. Fourth, the window for observation is narrow. Interstellar objects move fast. If you fail to catch them early, they vanish before you can study them thoroughly. And fifth, ambiguity breeds speculation. When data is incomplete, humans fill the gaps with imagination. Sometimes that imagination is productive, driving hypotheses and research. Sometimes it spirals into sensational speculation that eclipses the scientific narrative. Yet we also missed opportunities. With Oumuamua, there was no coordinated global response, no multi-platform observation campaign, no spacecraft dispatched to intercept or study it closely. We watched from Earth, analysed what we could, and then it was gone, hurtling back into interstellar space. With Borisov, the response was better. More telescopes participated, spectroscopy was more extensive, and data sharing improved. But still, there was no attempt at a close flyby or sample collection. Our response was reactive, opportunistic, rather than proactive and systematic. 3i Atlas represents progress. Multiple spacecraft, multiple wavelengths, planetary orbiters, and solar observatories combined to capture a rich dataset. It was a genuine multi-platform campaign, leveraging all available assets to study the visitor as thoroughly as possible, and yet, even this feels reactive. We're responding to targets of opportunity rather than building permanent capabilities for interstellar object monitoring. Every new visitor forces the same scramble: gather telescopes, retask instruments, analyze trajectories. The infrastructure for proactive monitoring and intervention is not fully in place. The real question is whether we will learn from this moment. Will space agencies treat 3i Atlas as a template for the future? Will they build permanent protocols, invest in dedicated infrastructure, and commit to transparency and data sharing? Or, once the excitement fades, will we revert to the status quo, passive monitoring, delayed data releases, missed opportunities? History offers a cautionary tale. Planetary defense has been a story of near misses and wake-up calls that were often ignored. Asteroids have collided with Earth before anyone noticed. Comets have passed closer than the Moon before we had the tools to track them. And threats could have been mitigated if only we had been paying attention. 3i Atlas might be the Rosetta Stone of interstellar observation. It could be the event that finally forces planetary defense into the mainstream consciousness. Or it could be a footnote, a curiosity in the astronomical literature, remembered only by specialists. Which outcome occurs depends on our response. Will governments and agencies invest in permanent proactive monitoring networks? Will international cooperation, protocols, and rapid response capabilities be established? Will funding be allocated to build dedicated spacecraft, AI-powered detection systems, and multi-platform observation networks? Or will we do nothing, hoping the next interstellar visitor is as benign as 3i Atlas? The stakes are not theoretical. Each encounter is a rehearsal, a chance to refine our understanding and preparedness. 3i Atlas offers lessons in coordination, observation, and analysis. It also offers a glimpse of the future. Multiple space assets, cross-disciplinary teams, and real-time data sharing can create a framework for planetary defense against interstellar objects. But without institutional commitment, the lesson may fade. Public attention is fleeting, and funding cycles often follow media cycles. The danger is that when the next object comes, whether benign like 3i Atlas, or potentially hazardous, we will be forced to improvise again, as we did with Oumuamua and Borisov. There is also the human factor. Ambiguity invites speculation, and speculation can shape policy and public perception. Oumuamua's unexplained acceleration sparked wild theories and intense debate. It drew attention not just from astronomers, but from the public and media. Borisov, being more conventional, attracted less sensational coverage, but provided a more grounded scientific lesson. Interstellar objects are detectable and can be studied in detail. 3i Atlas combined both. It presented an opportunity for rigorous scientific study, and at the same time provided fodder for speculation about potential hazards, the geopolitical dimensions of planetary defense, and the implications of detecting an object from beyond our solar system. Ultimately, whether 3i Atlas becomes a turning point depends on whether we act on the knowledge we gain. Will we create permanent observational infrastructure? Will we develop rapid response protocols? Will we invest in planetary defense technologies capable of intercepting or mitigating future interstellar visitors? The universe does not reward inaction. Visitors will continue to arrive, some harmless, some perhaps less so. Our preparedness, or lack thereof, will determine whether we can respond safely or whether we are caught scrambling at the last minute. 3i Atlas may be the event that pushes planetary defense into the mainstream, Or it may be another missed opportunity destined to be remembered mainly by scientists and enthusiasts. The outcome depends on whether we are willing to take the threat seriously before it becomes a crisis. It depends on whether we invest in detection, infrastructure, and international cooperation. It depends on whether humanity can learn not only from its successes, but also from its near misses. Because in the end, interstellar visitors are here to remind us of our smallness, our vulnerability, and the need to remain vigilant. And when the next visitor arrives, there may be no second chance. Part 15. Conclusion. Lessons, warnings, and open questions. So let's talk about what we actually know now, stripped of speculation and theatre. 3i Atlas was real. That fact alone should give you pause. For decades, astronomers watched the sky with one eye open, cataloguing distant objects, tracking near-Earth asteroids, occasionally sending probes to knock rocks off course. But 3i Atlas changed the equation entirely. It came from outside, carried velocity we couldn't have predicted, and forced every space agency on Earth to wake up and recalibrate what planetary defense actually means when the threat doesn't follow the rules. We now have multi-vantage, multispectral data on an object that originated beyond our solar system. NASA's satellites caught it. ESA's instruments tracked it. Mars orbiters photographed it. Solar and heliophysics missions recorded its interaction with the solar wind. That's not just a lucky break or a once-in-a-lifetime alignment of circumstances. That's infrastructure finally working the way it was designed to work. And the fact that it worked should terrify you, just as much as it should comfort you. Because it means we're now capable of seeing things we were blind to just 10 years ago. Which also means we're now aware of how many things we still can't see. The event itself was a scientific goldmine. Researchers gained real-world data on interstellar dust composition, magnetic field interactions, trajectory deviations caused by outgassing, and thermal signatures in near-planetary space. But it was also a wake-up call, because 3i Atlas didn't announce itself politely. It didn't send a postcard from the Oort cloud saying it was on its way. It just appeared, moving fast, already inside the decision window, where any meaningful response would require luck, preparation, and speed. And we got lucky. It missed. It didn't fragment catastrophically near Mars. It didn't deviate into an Earth-crossing trajectory. It just flew past, left some blurry photographs, and vanished back into the void. But luck is not a strategy. Here's where things get uncomfortable. The anomalies in composition, polarization, and dust behavior haven't been fully explained. Scientists have theories, they have models, they have peer-reviewed papers arguing for natural processes that could account for the data. But those papers also include phrases like further observation needed, and alternative interpretations cannot be ruled out, which is academic speak for we don't actually know yet. And that ambiguity leaves space for speculation, conspiracy, and all the wild theories that thrive in the gaps where certainty hasn't yet arrived. No verified evidence for artificiality exists. Let me say that clearly. Nothing we've seen proves 3i Atlas was anything other than a comet with unusual properties. But not proven is not the same as impossible. And that distinction matters when you're talking about objects that come from places we've never been and may never reach. What 3i Atlas represents is a paradigm shift. We've moved from passive astronomy, where we wait for things to happen and then publish papers about them, to active awareness, where detection, tracking, and potential response are treated as operational necessities. That shift requires infrastructure. It requires funding. It requires new policies that cross national borders and institutional rivalries. And it requires political will, which is the hardest resource to generate because it demands that governments spend money on threats that might never materialize. But the alternative is waiting until something does materialize, and by then it's too late to build the satellites, train the teams, or coordinate the international response. So here's the question that keeps circling back. Will space agencies embrace a permanent interstellar object early warning system? Will they fund it properly, staff it seriously, and give it the authority to act without waiting for committees to debate terminology? Or will this moment fade, replaced by budget cuts and shifting priorities, until the next object appears and we scramble all over again? And beyond infrastructure, there's the geopolitical dimension. Will international cooperation rise, driven by the shared recognition that no single nation can handle these threats alone? Or will competition and secrecy dominate, with countries hoarding data, protecting proprietary technology, and treating space defense as another arena for strategic advantage? Because if we can't cooperate on something as universally threatening as an interstellar impact, then we've already lost. Public perception will shape all of this more than scientists want to admit. If governments classify too much, people will assume cover-ups. If they release raw data without context, people will misinterpret it. If they say nothing, people will fill the silence with fear. The balance between transparency and responsible communication is delicate, but it's not optional. Open data, multi-agency collaboration, and public communication should be prioritized not as idealistic goals but as practical necessities. Because paranoia spreads faster than asteroids, and misinformation can do just as much damage as an actual impact. And then there's the human dimension, which is easy to forget when you're talking about orbital mechanics and spectroscopy. Space is vast, unpredictable, and fundamentally hostile to life. But we are no longer helpless. Our growing ingenuity, our expanding network of sensors, our improving ability to model and predict, all of that can turn cosmic mystery into manageable risk. Not zero risk, never zero, but manageable. Which is more than any previous generation could say. So whether 3i Atlas was a cosmic messenger, a comet, or simply a strange visitor from a place we'll never visit, it doesn't actually matter. What matters is what we choose to do next. Because in the dark between the stars, vigilance might be our greatest defense. Not weapons, not walls, just attention. Just the willingness to look up, stay curious, and refuse to pretend the universe is safer than it actually is. Stay curious, stay skeptical, and stay ready. Because if humanity wants to survive, not just on Earth, but as a species aware of the cosmos, this may be the moment we truly begin to listen.